Hi, this is CrossDot and Nabla, and in today's video we're going to be going over section 12.5, covering over the chain rule for multivariable functions. And before we start off with anything related to the chain rule of multivariable functions, let's go back to Calculus 1, like we so often are going back to in this video series, and recalling the chain rule that we had prior for a composite function f of g of x equaling this, right? And we could also rewrite it as this as well. And that's important to show up later on, right? So say we have some y equals cosine of 2x. Well, our outside function is just going to be f of something, which is just cosine, and then our g of x is going to be our 2x, and then we can just say y prime equals negative sine 2x. We keep the inside the same, take the derivative on the inside, we get 2, and then we get y prime equals negative 2 sine 2x. That's relatively trivial for the level of math we're at now, but it's an important foundation that we are going to build off of for this video right here. The first thing we're going to look at is if we have a parametric function for x of t, y of t for z, and we've seen those somewhat often in chapter 11, right? And we take the derivative with respect to z, take the derivative with respect to t, excuse me, we get del z del x. Now this is important to understand because z has two inputs to solve for it. That means you're taking the partial with respect to x and you're treating y like a constant. You're not doing dz dx, you're doing del z del x because z relies on both x and y. It's not just one. It relies on both, right? However, the dx dt still remains the same because the x of t, x is only relying on a single variable or a single parameter, t, right? And the same thing for del z del y. Z relies on both x and y. It doesn't just rely on one. In single variable calculus, it would be like something like this, y equals f of x of t, which then you could say, let's rely back on this chain rule up here. In this class, we can't say the same thing, so we have to take the partial instead. And this right here is dz dt, not del z del t, because z only is changing by one single parameter, one single variable, which is t, right? And we can look right here, and we can see that we have this new symbol called nabla, or the del operator, which is just like taking the derivative of something or taking the partial derivative of something. And in fact, we're actually dotting it. This is the dot product with dx dt, comma dy dt, because this is also a vector, right? And we're seeing it as that, right? This right here is a vector operator as well. And this f corresponds back to this right here. And when you do del of f, what you're really doing is del of dt. No, you're not doing del of dt. You're doing del of dx dy del y and multiplying it by f like this. And then when you multiply this out, or when you dot this out, you get the resultant right here. And you can see like the flow chart of this. Z has to rely on x and y, so that's why you take the partial with respect to x and y. but x and y both only rely on one single parameter, t. Similarly, we have x being both dependent on s and t, and y as well. They have first partial derivatives at s comma t, and we let z equal f of x, y be differentiable at x, s comma t, y, s comma t. Pretty straightforward stuff, right? We can't have any like infinity discontinuities and such. So we do this, but a couple of things to notice is that it's going to be del z, del s. Now again, this is important because before we said z was only dependent on this t right here because y and x were dependent on it, right? But now z is dependent on both s and t. And in this case, if you're taking the derivative with respect to s, the t is left as a constant. So you're taking a partial derivative with respect to t. And again, x is also a partial derivative with respect to s because it's going to be dependent on s. So like we said earlier, del z del x is the same thing up here as it is down here because it's dependent on both x and y. And then same thing for del y del z and del y del s because x and y now are both dependent on s and t. It's kind of like it's the exact same logic that we used for saying that this would be del z del x, right? Now going to example 1, we have this right here where we have find del w del t given w equals x squared y minus y squared x given the constraints that x equals cosine of t and y equals sine of t. Express the answer in terms of t. Now you could do a couple of things. You could just substitute in x for cosine t and y for sine t. However, given our new knowledge of this chain rule, we can try something a little bit different, right? Feel free to pause the video and try this problem on your own. Let's get right into it. So yeah, let's get right into it. So to me, del w del t equals dw dx d del x. Actually, no, sorry. It should be del w del x dx dt plus del w del y dy dt. And let's just get all of our stuff out of the way. So del w del x is going to be 2x y minus y squared dx dt is going to be negative sine of t plus del w del y is going to be 2x minus, actually no, it's going to be x squared minus 2xy cosine t. And now we can substitute everything back in. So then we can get x equals cosine t, y equals sine t. This is going to become 2 sine t cosine t minus sine squared t negative sine t plus cosine squared t minus 2 sine t cos t. And then we can distribute everything out. We get negative 2 sine squared t cosine t plus sine cubed t plus cosine cubed t minus 2 sine t cosine squared t. And that is our answer for del W del T, or dW, or del W dt. Perfect. Example 2, find del W del T given W equals ln x plus y minus ln x minus y, given these parameters for x and y. This is going to involve the second theorem that we learned. And if you want to pause the video, try this on your own, feel free to do so. And let's get right into it. So we have del W del T equals del W del x dt plus del W dly and then we have del W del x, which is just going to become 1 over x plus y minus 1 over x minus y. Dx dt is what? It's going to be, take the derivative with respect to t, it's going to be e to the s. Del W del y, it's going to be 1 over x plus y minus negative 1 x minus y, so plus, times t is the variable we're differentiating with respect to, so I'm going to take the derivative of e to the st, so it's going to be s e to the st. And now we can plug in x and y everywhere to solve for the partial derivative. All right, let's see. This should become 1 over TES plus EST minus 1 over TES minus EST all over e to the st, all over e to the s, excuse me, plus just copy this over because it's the exact same thing, barring the positive, just need to flip that. And that is your answer for example number 2. Example number 3. This is another example. Again, if you want to try this on your own, feel free to pause the video. This will involve a lot more plugging and chugging because you're actually getting a value from the chain rule. And yeah, let's get right into it. So again, we're going to apply the same rules that we did before. It's going to be del W del T equals del W del X del X del T plus del W dy del y dt. Del W del X is going to become, y plus 1. Yeah, y plus 1. Del X del T is going to become 1 plus del W del y. This becomes x, this becomes 1. And then del y del T is rs. Yep. And then from here, we can start plugging everything in. So we're going to get RST for our y. This is essentially negligible, plus R plus S plus T plus 1 times RS. RST, so 1 times negative 1 times 2. This becomes negative 2 plus 1 plus 1 minus 1 plus 2 plus 1 times r times s is just negative 1 times 1. It just becomes 1. This cancels, plus negative 3 times negative 1. So you get negative 1 minus 3 equals negative 4. And that is your answer. Example 4 is going to kind of go back to related rates from Calculus 1. Might be a topic that a lot of people don't like. I personally enjoyed it a little bit. It required me to think more out of the box. And yeah, for this example right here, we have sand is pouring onto a conical pile in such a way that at a certain instant the height is 100 inches. It is increasing at 3 inches per meter. The base radius is, at that instant, is 40 inches and increasing at 2 inches per meter. So before you even start off, I'm going to try and visualize this myself because I want to see what the heck is going on with this problem. So we have this, and we're building some sort of conical shell, right, or conical pile of sand, right? So let's get that. Let's get some of our units as well. So we have our radius is changing at our del r del t equals 2, our r equals 40, our h equals 100, and then del h del t equals 3. And we know the volume equation for a cone is 1/3 pi r squared h. Let's get that down. And now let's just take the partial with respect to t. And then we have to invoke the chain rule because we have multiple variables involved. So we have del v del r times dr dt. Since t is the only variable in this case, it doesn't have to be del, right? Then we have del v del h times dh dt. And then we can plug in our new part to the equation. So we have this becoming 2 pi over 3 RH dr dt we said was 2 plus dv del v del h is going to be 1/3 pi r squared times del dh dt, which we said was 3. And then from here, we can plug in everything that we know. So let's just factor out a 1/3 pi real quick. That's going to be 4 plus 3r squared. And then we can do 3 times, so we're going to do 4 times 40 times 100. This is going to go to 16,000 plus 3 times 40 squared. This is going to become 1,600. It's going to be 4,800. And this is going to become 20,800 pi over 3 as our final answer for del V del T. And don't forget your units. It's always going to be inches cubed per minute because it's a volume. And yeah, perfect. One other topic we will be going over in this section is implicit differentiation with the chain rule. This is something that we learned in Calculus 1. We had to do a lot of problems with this example right here. And it's not terrible. It just takes a bit of time to like isolate for the dy dx and get everything by itself. So that's more frustrating than anything. However, there is a shortcut that we will be going over in this video later on. But yeah, let's just do this example real quick and read back on it. So this is going to become 3y squared dy dx minus 2y minus 2x dy dx, because y is, because you need to do derivative of y with respect to x, it should be dy dx. And then plus 3 equals 0. So then we get 2y minus 3 equals dy dx 3y squared minus 2x. Take the derivative and isolate for dy dx. And that is your answer for that part. We can apply the same idea to this right here, and we're just going to solve for del z del x. And we're going to treat anything that's not x as del z del x, right? And we'll just go through like that, like we did right here when we had something like y cubed, and we took the derivative with respect to x. It's going to be take the derivative of that, but then we have the del z del x, or the dy dx attached to it, excuse me, right? So let's apply this new rule right here. So we're going to do del z del x. So then we're going to get y cubed plus secant y plus z tangent y plus z del z del x, and this is supposed to be a zx squared. And this is going to become minus x squared equals 0. Then we can isolate for, oh wait, no, this is supposed to become minus 2xz, like that, equals 0. And just making sure we have everything down here. Yeah. And then we have 2xz minus y cubed equals del z del x times secant y plus z tan y plus z, divide everything over, and then we can get our answer for this new expression. And example 5, this is going to involve the chain rule again. And if you want to try this example on your own, feel free to pause the video. Let's get right into it. So we have del z del x. So just take the partial with respect to x everywhere. And we're going to get negative y e to the negative x here, plus cosine x plus z, take the partial on the inside, going to be 1 plus del z del x plus e to the z del x equals 0. And let's just isolate for everything that we know. So we have cosine x plus z minus y e to the negative x. And then we have plus cosine x plus z plus e to the z del x equals 0. And we can subtract this whole quantity over. And then we get y e to the negative x minus cosine x plus z equals del z del x. Divide everything over. And that is the partial of z with respect to x as our answer. And then we can apply the same ideas for taking the partial of z with respect to y. So then we can get e to the negative x plus cosine of x plus z. Take the derivative of the inside, it's all going to just become d del y del z. Del z del y. Yeah, del z del y plus e to the z del y equal to 0. So then we're going to subtract e to the x on both sides. We're going to get negative e to the negative x equal to cosine x plus z plus e to the z del z del y. And then just divide everything by cosine x plus z plus e to the z. And then you will get your partial of z with respect to y. And this section is a lot of heavy algebra, so it's always something to be conscious of if you're struggling with your algebra. This section may be a little bit more difficult to go over. And yeah, it's a lot of algebra, a lot of making sure you're taking the right partials with respect to the right variables, making sure that you have del instead of d or d instead of del and vice versa, right? Being conscious that's always important, because on exams, your professors will always dock off points for that, because it is a meaningful distinction, right? And one last thing we'll go over in this section is related to implicit differentiation for functions of two variables. Is if you want to solve for dy dx, there's another way you can do it. It's a nice little trick. So if you have a function f of xy equal to some k, some constant, right? Take the derivative with respect to x. You're going to get del f del x, and you're going to apply the chain rule here, del f del x times dx dx plus del f del y times d times dy dx equals 0, because k is a constant. This goes to 1. Del f del x equals negative del f del y dy dx. And we can rewrite this to say it's going to be f sub x equals negative f sub y dy dx. Divide both sides by negative f sub y. And we get negative f sub x over f sub y equals dy dx. And that's a cool little trick to save yourself some time for problems like this. And we're going to actually use that in example 6 right here. So if we want to solve for dy dx when f of x comma y equals sine xy plus pi y squared minus x. So we'll just do f sub x equals y cosine xy minus 1. And then f sub y equals x cosine xy plus 2 pi y. Then we just substitute that into this equation right here, this expression up here. And we get y cosine xy minus 1 over x cosine xy plus 2 pi y, all equals dy dx. And that is pretty much it for this section, for the chain rule. Thank you so much for watching, and I hope you guys all have a fantastic day.